Welcome to the ECS podcast. I'm Rocky Calvo, Executive Director of the Electrochemical Society. The purpose of this podcast is to connect the dots between the sciences, our everyday lives, and the sustainability of the planet. Our guest today is Johna Leddy. Johna heads the Leddy Lab at the University of Iowa, where she and her students conduct research in areas such as batteries, fuel cells, and the characterization of mass transport in films. She's been an ECS member for 36 years and has held numerous positions and spent numerous hours in committees and boards and all sorts of things. So welcome, Johna.
Thank you, Rocky.
We always like to start this thing out by asking you a little bit about what interested you originally in pursuing the sciences. You spent your life work in the sciences, and what kickstarted that?
Well, my dad's a chemist, and there was always fun with puzzles and numbers in the house. There was occasionally even science night, but my mother would leave.
Anything else?
Oh, well, my brother's an engineer, so we just always had a family kind of perspective on things from a let's see if we can figure it out approach to questions.
And how about, as you got into high school and influences from courses you took, people you met, things you were doing at the time?
Okay, so from the time I was about 5, I wanted to be a mathematician, and then I couldn't figure out what mathematicians really contributed. So I ended up doing chemistry because I could also do my math. And so.
I see. So I think it's in the blood.
It's genetic.
And I get the sense from our conversations that it's continuing to be in the blood with your family.
Yes. They seem to enjoy those kinds of puzzles.
Okay. Well, then let's go a little more formal. You pursued it academically. Tell us a little bit about your undergraduate and graduate experience.
Okay, so I was an undergraduate at Rice, which was really nice because there was a lot of emphasis on making sure you have an equation to go with whatever it is you're trying to describe, and I met some similarly minded people, and that was good. My brother was there too, and then I went to graduate school at the University of Texas. I was in Al Bard's lab. And that was an interesting experience because at that time there weren't really a lot of females in graduate school. And then I was a postdoc in Los Alamos in the fuel cell program when fuel cells were starting to get launched. So those were all very different experiences, but all excellent parts of what it is I have turned into as a scientist.
And when you say Rice, my mind goes to ECS connections now, because at the time you were there, well, I should ask this question. Was Norman Hackerman president of that university at the time you were there?
Yes, he was. And he would often, I used to teach the freshman labs as I was a junior and a senior, and he would come in with his bow tie and walk around the room and talk to all of the undergraduates, and then he would leave and they would all go, "Who was that?" "Well, that's President Hackerman." So that was great. He would ride his bike around campus. And you had to pay attention so you didn't get squished.
He was an influential man in my career too here at ECS. He was the editor for 40 years. Concluded his service around 1990. So I spent the first decade at ECS as under his tutelage because his sheer personality and influence as the editor of our flagship journal made him one of the more significant leaders in our organization. Did he have an influence? Obviously, as university president, he's not working one-on-one with students, pursuing a whole lot of research interests. But did he influence the science, the students, the departments at Rice?
Not so much directly, but there's lots and lots of science students at Rice, and so but he always made a point to come down and visit with the freshmen in the freshman lab every semester, and I think that speaks to his focus on helping the students to become good scientists and just being a good role model, a good guy.
Who was your mentor at Rice?
Let's see. So I worked with Lon Wilson actually. And Lon is very much involved with our fullerene groups. I still see him occasionally at meetings at the ECS meeting.
Yes, the Fullerenes has probably been our most significant symposia that we've held from year to year for maybe the last 15 years. So, and he's still a participant. After Rice, you go to the University of Texas,
Yes.
Alan Bard's lab.
Yes.
Another legend you encounter, an ECS legend, and Alan Bard. What was your experience like there?
Well, at the time, really, there were not that many women in graduate school, so it was not infrequently that I was the only female or one of two females in a group of 35 people. So it was unique.
Unique how?
Well, it was, nobody really understood how to incorporate women into the scientific enterprise, because it was a different idea at that time. And so it was not that people were hostile. It was just that people didn't know how to interact. So, and they all tried. So that was a good thing. When I was there, I got to meet pretty much everybody, because everybody would eventually wander through the Bard Labs. So,
right. You've spoken often of your family tree. Who was with you? Who was among the 35? That would be familiar names to all of us.
Let's see. So Henry White and Hector Abrunia and I shared a lab bench, and Dick Crooks was there. Chuck Martin was a postdoc at one point, and Tito was a postdoc as well. So
everybody you just mentioned is at least a fellow and has won some major award in ECS. So you must have had a heck of a group.
It was never boring.
Well, the story about family trees and connections to ECS is always interesting to me. I'm just from your speaking to me about it, I get a sense that it influenced your career, the success you've had, but it also influenced your participation in ECS.
Yeah, oh, definitely. So one of the reasons that I did survive as a scientist was because I had a couple of older brothers in electrochemistry who took an interest and tried to help along the way, and that would be Larry Faulkner and Joe Malloy. And so and of course Larry has been very involved with the ECS for many years. And
Joe Malloy was at one time as well. I believe he was an old divisional editor in the days we had those positions.
Yes.
He was at Seton Hall, I want to say.
Yes, I mean, he's still there. So.
Oh, he's still there.
Yeah.
Okay, so maybe we'll move along and ask about your postdoctoral experience at Los Alamos National Lab.
It was very early in the fuel cell game, and I worked with Nick Vanderborg at Los Alamos, and there were Shimshon Gottesfeld was there at that time, and Srinivasan. So they were all, that was a nucleation point for a lot of the early fuel cell work. Ian Raystrick, good group. And at that time we were characterizing membranes and trying to figure out catalysts and how Nafion worked and, how we could make it better. That was the domain of activities.
How long did you do the postdoctoral work at Los
I was there for 2 years.
Mm-hmm.
And it was the time when they were moving from phosphacid fuel cells into hydrogen, oxygen, and PEM fuel cells. So.
And then what?
Then I joined the faculty at City University of New York, Queens College, and I was there for about 5 years. And that was a very good group to work with, good people.
And closer to home, being a Jersey girl that you are.
Yeah, well, by that time, my family had already moved to Texas, so they moved when I was in college. So.
Oh, okay.
Yeah. But I can transmit that at a significantly high baud rate. So.
And from City University to University of Iowa.
Yes. I moved to Iowa in 1991.
So after this many years at the university, and obviously your career has been primarily focused on academia. What made you choose that route, and why'd you stay?
Well, when I was coming to the end of my postdoc period, which I enjoyed very much, and it gave me lots of nice opportunities. This was when I went to my first ECS meeting, for example. the decision was I going to try to stay at a national lab? Was I trying to go into industry, or did I want to go into academics? And academics had always terrified me, mostly because I was morbidly afraid of speaking in public. When I was in graduate school, we were having a meeting about polymer-modified electrodes and how to characterize them. And we're sitting at this table, and I had been working on a model for something, so lots of equations, right? And there were two projection screens in front of the chalkboard, and I'm at the chalkboard, and I keep writing on the chalkboard, but I keep walking behind the projection screen, so just my arm is sticking out, and this voice is occurring, but I cannot be seen. And Bard keeps jumping up and pulling me out from behind the projection screen. This happened 2 or 3 times in a 20-minute period, okay? So I really did not want to be heard. I didn't mind being heard. I just didn't want to be seen.
That would have been a fun scene to see.
Oh, Lord. So I've come a very long way. But I decided that I would check out the academic branch, because at that time that was, if you were going to do it at the end of your postdoc, was the right time to go into academics. It basically came down to I wanted to work on what I wanted to work on, and I didn't want anybody else to tell me what to do. So,
and so, go ahead. I'm sorry.
I paid the tax of learning how to speak in public.
Was there a mentor or an influence that helped lead you to become an educator?
I have had some excellent support over the years from different folks who were in the academic environment, and I think that they weren't bored, and it's important not to be bored. So. Mm-hmm. It looked like an interesting puzzle at the time, so that's what I did.
And I'm sure you found it to be an interesting puzzle.
Oh, yeah.
How is academia different than the national labs?
I think it's the diversity of things that you focus on. So at a national lab, it's not quite as broad, because you don't have students to a large extent. You're definitely not teaching freshman chemistry, and the amount of committee work is probably significantly less than you would have in an academic environment. So your focus is you've got more stuff going on in academics, and so there's that as part of the component for what's different from a national lab. Because a national lab, you're usually focused for at least a year or two on a specific type of a problem. But in academics, you're teaching, and you've got committees, and your students are wandering in and out, and there's also committees on campus, and your time gets chopped up more.
From the perspective of successful research, do you think that the national labs are more enabling, allow more flexibility?
I think they're different. So an academic route is kind of a more traditional route. We kind of know what scientists, professors do. But a national lab, they are more intensely focused in general on a specific problem, and that problem will evolve over years. But it is more focused. The overhead on doing research at a national lab, cost-wise, is very, very high compared to an academic environment. But you're supporting, well-vetted, mature scientists to work on projects, whereas in an academic lab, you're trying to help people learn how to think about problem solving and identifying a good problem and going after it. So it's got a different incubation period.
Right. The thing I was trying to poke out a little bit was, we've done a podcast on Bell Laboratories, the invention factory, right? And there was a lot of discussion and comment about how that was built, and how they had a certain amount of freedom and, of course, funding, and how there was a different type of opportunity they without the pressure to produce a certain result, or and of course I'm talking about until the Bell Laboratories broke up, and with the AT&T monopoly in 1986, I believe it was. But I heard others compare the national laboratories more to that model than a university campus can afford actually to accomplish. So any comment about that?
Well, in academics, the competition for funding and support of research is pretty intense. I mean, people spend a lot of time trying to get grants funded and so forth, and that's time. It's good time to think about things, but but it adds to the tension of trying to do high-quality research. National labs, they do have internal funding mechanisms and government support of different kinds, but once upon a time, like Bell Labs, there was, it was easy to get funding. It was easy to get funding in academics too, but it's not like that anymore. And I think across the board, people have to spend a certain amount of attention on making sure that the resources are in place to do the science.
Yeah, so it's fundraising essentially, as opposed to actually conducting the research, and that's takes away from the opportunities and time to do so.
Yes.
Let's talk about your laboratory, the Leddy Lab.
The Leddy Lab.
And where it might have gotten its name.
I can't imagine.
When did that occur?
When did we get that name?
Yes.
So the students kind of named it.
Great.
Yeah, my colleagues call them Luddites. So, but I would, yeah. So I think that's just kind of the way labs are named. They're named, after the faculty member who's, kind of standing by.
Mm-hmm. And I think this is the most important part of this, and all the podcasts really are trying to connect the dots. So what we want to find out is what you're doing in the laboratory and how that's making the world a better place.
Well, that's always an important objective, right? So we tend to look at different kinds of catalysis, how to improve electrocatalysis, but we don't necessarily look at it in the way that people would typically look at it, wherein they would design a catalyst from a chemical perspective. If I make this oxide with this metal, can I drive this reaction faster, or prohibit a reaction, depending on which way you're trying to go. But we look at different ways to physically manipulate the system so as to increase reaction rates. And so a few of the ways we've done this is to, for example, put micromagnets onto an electrode surface, usually in a layer of Nafion on an exchange polymer, and then look for increases in rate, which would manifest as higher currents with lesser voltage driving forces, so that you would end up with a higher rate. And in general, we've looked at this, in academically interesting systems at modified electrodes. We've looked at this in fuel cells of various kinds: hydrogen, oxygen, hydrogen, air, hydrogen with CO contamination. We've tried to look at some direct reformation, and that was less successful in that context. We've looked at it in several different kinds of batteries. We've used magnetically modified electrodes to generate hydrogen with a 6% photoconversion efficiency at a magnetically modified P-silicon electrode. We've looked at supercapacitors. Pretty much we've looked at a wide range of different types of electrochemical energy systems, and generally speaking, if we put micromagnets into the system, we can increase reaction rates by about 40%, typically, for a full system. And another type of experiment that we do, we use ultrasound. So one of the weirdest things I ever heard was if you irradiate a fluid with ultrasound, you first compress the fluid, and then on the next half of the wave it pulls apart, and then it comes back together. And when it pulls apart, it makes a void, and when it comes back together, it collapses that void. And right at the interface between the void and the solvent around it, you get extreme temperatures and pressures, like 5,000 Celsius and 1,000 atmospheres of pressure. So if you want to increase a reaction rate, that would be a great way to do it, if you could capture that at the electrode. And people have used ultrasound in electrochemistry before, but they've usually done it in a bulk phase. So what we're doing is to use the ultrasound in a thin layer so that the energy cannot dissipate. The energy will tend to stay at the denser phase rather than partition out into the gas phase. So we can get all of that energy and capture it from 3 dimensions in the thin layer into 2 dimensions at the electrode surface. And we can catalyze some of those reactions that in a fuel cell are often a problem and our magnets didn't fix. So we can increase the rate of oxygen reduction substantially in a thin layer sono-electrochemical cell, and we can actually see some significant currents pass the electrolysis of alcohols. So that's a relatively new project, and we're working in that domain. We have a third project where we've put algae on electrodes, and of course Nafion, and we use this to generate ammonia, because the algae has the mechanism to break nitrogen-nitrogen double bonds and other mechanisms for making ammonia. Those are the principal things that we're working on right now.
Can you give us a little insight, some of the practical uses of some of the research that you just discussed?
Okay, so if you want to have a more energy efficient economy, then you need to have better catalysis for those processes. So any place you have an electrochemical power system, one of the advantages is that there is, unlike a combustion engine, for example, where there are moving parts, an electrochemical system can be 100% efficient from a theoretical perspective, whereas a combustion engine can only be about 40% efficient from a thermodynamic perspective. So there's a lot of room to make a more efficient system if you can make it work electrochemically. And so that's an inherent advantage. Fuel cells, hydrogen, oxygen fuel cells and so forth, typically under operating conditions run at better than 60% efficiency because there's no moving parts. But if you could capture some of that additional energy, not wasted as heat in the electrochemical power sources, then you would have yet a further improvement in the efficiencies for the system. So the ideas that I explained about the magnetoelectrocatalysis and the thin layer ultrasound represent two mechanisms where you can inherently improve the efficiency of electrochemical energy systems from a fundamental perspective. We don't entirely understand what's going on, but the message is consistent that we can use these mechanisms to reduce the energetic cost to drive electrochemical reactions. And so it turns up, and we can demonstrate the magnetic effects in batteries and fuel cells and solar cells and photovoltaics and supercapacitors. And the sonochemistry, we're at the point of looking at different types of reactions, and we see significant effects on reactions that slow down electrochemical processes and therefore reduce efficiency. So we can improve the rates of electrolysis for oxygen and the rates of electrolysis for alcohols. And so that speaks well to being able to build better integrated systems such as fuel cells and batteries and so forth with these types of manipulations.
Lots of important stuff going on in the Leddy Lab. How many students do you have working?
Let's see. Right now there's about 5 graduate students right now, and one of them is from the math department.
Yeah, I thought you were going to name a number, maybe 3 or 4 times that.
No, they're very busy.
And where they come from? The work you're doing is so hot, relevant, attractive to, I'm sure, students. Where are your students coming from?
So right now, let's see. One student's from Colorado and one's from Georgia. One is from Minnesota and one is from, all over the place, but near Iowa at this point. And one is from Sri Lanka.
And so, when they finish their work in the Leddy Lab, can you just tell us a little bit about some of the things that they've done?
So my students have gone off, and some have gone to work in academics, some have gone to work at national labs, some have gone to work for big companies, some have gone to work for startups. So there's a whole range of things. The ones who go to work with startups, they've usually had experience with patents while they were in the group, and that has served them well in their next steps. Some have gone to work for big companies, Samsung, DuPont. And they're integral to the research teams that are at those larger companies. At least one of them is recently joined a national lab as a permanent staff position at Oregon. And let's see. So I have 3 students who have gone into academics. One of them is Lois Zook at Muskegon. And another one is Luke Haverholz at Bradley, and then Shelley Mintier is at Utah. So I think that most of them are leading a life that they're pleased with, and so that's a good thing.
Must make you very pleased as well.
Yes.
And so 24 years there, you've got a pretty good-sized family tree going yourself now, don't you?
Yes, and they're off making their own academic children now, so it's good.
As I said, it must make you feel very good to see that.
Yes.
I want to change gears a little bit after you're sharing what you've been working on with your lab and just talking about it maybe from a more general sense, because you work closely with in the energy field. And so what are your thoughts on the future of our world energy infrastructure?
So I think that the history of the world and all of its conflicts are all about energy, going all the way back to trying to take over somebody's farm because the farm was about generating energy. And I think that energy component has driven all the conflict that we have. It drives the conflict that we have now because the energy is localized in certain places, but it isn't accessible uniformly everywhere. So if you can figure out ways to distribute the energy, to take advantage of renewable energies, I think those are opportunities to not only give people a better life, but also to give them a more secure life where the conflict over energy is reduced. So I like to explain it this way. It's all about power. If you have power, you can have water. If you can have water, you can have crops. If you have crops, you can go to school. If you can go to school, you can find out the guy next door isn't so terrible after all. It's all about power.
I like your explanation of all of this. It's very simple and clear. And so to get there, what do you think are some of the biggest challenges we have to deal with for clean energy?
Thermodynamically, the first rule of power sources, as far as I can tell, is that if it makes a good bomb, it makes a good power source. Otherwise, it's not worth building the power source because you can't get enough energy out of it. But then the trick becomes, how do you harness all of that energy? How do you allow it to be provided without actually blowing things up? And so electrochemistry is actually a very good way to do that, because you're discharging the energy electrochemically as opposed to thermally, and that will tend to minimize the number of runaway events, explosions. So that's a very nice advantage to electrochemistry. The challenges then become, how do you build such a system so you can harness the energy effectively in an electrochemical manner? And so that brings in challenges about catalysis, and how to build a good system. How do you make good catalysts? How do you build a system that's simple so everybody can have one? That means cost is an important part. Platinum is a wonderful material, but it isn't necessarily it's not ubiquitous. It's a costly material. Could you build a system that uses a catalyst that is more accessible to everybody everywhere? We have carbon dioxide. That's really, thermodynamically, that's not a winning scenario. So a good way to proceed to minimize the carbon dioxide that we generate would be a major advantage. And so electrochemical systems do give you that advantage if you can get them to run with good efficiency. So the challenge is nice electrochemical systems with good electrocatalysts in a simply designed system that everybody can have it, so we can distribute the power and reduce the conflicts over energy.
Right. So, and if we do that, we can create the world you described earlier, and that's going to require, I guess, leadership from our government. Do you think that we should be doing more to carry the message from the scientists to the governments? I mean, what more can we do?
Well, I think that having a good communication train is absolutely essential to that. We have a fair number of folks at the Electrochemical Society who are involved with government, and they interact extensively with the scientists. And I think that that's one of the great things that ECS is able to promote. Should we have more of that? Oh, most definitely. It would be having a better understanding of what the government thinks the questions are, and for the government to have a better understanding of what the scientists think might be reasonable solutions. That's an important part of this process. Another part of the process is that the communications between the scientists and the government, they're already intimately mixed. So the government, comes up with a research problem, and then they provide money to the scientists to explore that research problem. And then the scientists report back, and the government needs to assess what the scientists have said. The scientists can also design the next research question. But the old model was that, government sends money to scientists, scientists do work, publish papers. Published papers are peer-reviewed, and then the government can look at those peer-reviewed papers and be able to determine whether or not the scientific undertaking was effective or not. But right now our publication mechanisms are not what they once were, and I don't think that the government necessarily recognizes that there has been a transition. So right now the premium is on getting the publications processed quickly, and the emphasis is not necessarily on the quality of the review. And if the government is, you can buy a paper now, okay? You can just send somebody $500 and they'll publish your paper. If the government is not savvy to the quality of the review, then the metric is broken, and I think that should be communicated, because it's an issue of some concern. If I have 15 publications, and if the government says, oh, look, 15 publications, that doesn't necessarily say that science was well vetted by their peers, the scientists' peers.
Mm-hmm. Well, yeah, you're beginning to touch on a topic that really hits close to home at ECS as a scholarly publisher, and all the change in publishing and all the ramifications and the opportunity both of all these changes. And you just described one at a government level, which is really critical if the government is going to be making the right decisions about well, in our case, we're talking about decisions affecting clean energy and our future.
Yes.
Changing gears just a little bit, because I started thinking about some of the things that you've done with ECS, and you have had so many positions. I can't even begin to describe some of the things. I want to hit some of the highlights before we conclude the podcast. But one thing I recall was some of your work with us when we had to communicate this type of message through the Federation of Material Societies, and we were trying to connect the dots again so that we could inform. These were Capitol Hill visits that we used to conduct with FMS, and you were one of the key authors about writing that message for us and communicating it, through the Federation of Material Societies to get it on Capitol Hill. So you've been wrestling with these questions for a long time. Do you remember that work?
Yes, I do remember that there was lots of discussions about how to get the government to understand what the constraints were and how things are changing.
We're not working with the Federation of Material Societies anymore because of some differences of platform, opinion, direction, I guess, by the member organizations. Actually split up FMS and well, it's ruined the alliance we had, actually, and an avenue. But ECS is doing more in the way of trying to communicate the importance of electrochemistry, and not just at a government level, but to the public at large, and well, certainly our community of scientists.
I think certainly the public is hungry for more efficient energy systems, because everybody is carrying 5 batteries with them on average just when they walk out the door in the morning, and having those be efficient and being able to reduce the expense both environmentally and cost-wise for generating energy, which is what we're all driven by. That's a core interest, because that defines how people's resources are used and what it is that they're able to accomplish with their resources.
That's right. And when doing these podcasts and talking to people like you, you can get a feeling and an understanding of the potential. There's a really great opportunity for all of us out there. So I want to thank you for sharing that part of this podcast with us.
Very good.
So I always like to hit the ECS things a little bit, and we've talked about it just briefly, and again, you've done so many different things with us. Maybe it would be best to ask you if you could tell us about what you thought some of your highlights were at ECS, work that you did, roles that you played, and how that influenced your career, your life, and whatever.
Well, I would say that there are times when the career path is difficult, but there is no doubt that it is a very privileged life, and that privileged life is in an opportunity to work on significant problems and to communicate with students and help to form how they ask questions and move forward. But a big part of that has always been ECS. So it has provided lots and lots of opportunities to know lots and lots of outstanding, excellent scientists, and to have places to go when you have that question that you can't get an answer to, and to have wisdom that's available for how you might address various kinds of problems, not just science, but how to live in academics, that type of a thing. And so it's always a nice opportunity to give back, to support that opportunity for the folks who come next. Give respect to the folks who came before. It's integrated over all of that space, and it's integrated over the science and the colleagues and the opportunity to make the world a better place, because it's a rare opportunity and it is muchly appreciated. And ECS has always been part of that, because it's a big part of that, because it's the venue through which all of these interactions are orchestrated.
Well, that is a great way to wrap up this podcast, but I just don't want to stop there, because I do like to give you the opportunity to share any final thoughts that you have. And it's going to be hard to beat your last couple of thoughts, I have to say.
Well, from a personal perspective, I am not bored, and I acknowledge the privilege that this life has provided, and I know that it is important that we address a lot of these energy concerns, and that everybody should give it their best shot, and it should not be petty, because it is important. So.
Well, then, thank you, Johna.
Thank you, Rocky.
That was Johna Leddy, an Associate Professor of Chemistry at the University of Iowa and an ECS Fellow. And we really appreciate you spending the time with us today. Thank you very much.
It has been fun.
You can find the University of Iowa Department of Chemistry at facebook.com/UI Chemistry. You can find ECS on Twitter at ECS.org. Listen to more episodes of our podcast by searching ECS Podcast on iTunes, or just go to our website, electrochem.org. Thanks for joining us today.